In this example, we have a diffraction grating. And a diffraction grating is essentially like a double slit, but instead of just two, you have many openings for the light to pass through. And those openings are spaced very close together. Diffraction gratings are typically labeled in lines per millimeter. So I have one right here. Here's a diffraction grating. If I wave it around, you might see like rainbow colors in it occasionally, if I tilt it at the right angle. So this one clearly says it's 1,000 lines per millimeter. That means on this screen, you can't see them with your eye, but there are lines or slits 1,000 per millimeter across this screen. Okay, and I can prove that to you. This just is not a clear screen by wiggling it around, and you can see the rainbow pattern. So it's spreading out the light beams. I can show it a little bit more directly with the laser pointer. All right, so if this is the laser pointer, you get one dot. Okay, if I put it through here, you'll see, it's hard to do this. If I can make you see it and also see the pattern. All right, so you can see that there are multiple dots there, right? So you can see the first, so the central maximum, and then the first order maxima on either side of it, right? So this is spreading out the light. Notice that it looks a lot different than the one for the strand of hair, right? Where the pattern wasn't nearly as sharp and like it wasn't as sharply defined. It was a little more blurry and it wasn't quite as bright. What a diffraction grating does is it doesn't change the locations of the bright spots. That's just determined by how closely together they're spaced. Doesn't matter how many there are. But it changes how bright they are and how much cancellation there is, how much destructive interference there is in between. So there's no blurriness. There's kind of just these sharp lines. Okay, so that's what a diffraction grating will look like. So in solving a problem, you'll typically, with diffraction gratings, you'll typically be given how many lines per millimeter. So this one's 1,000. And then you can calculate the spacing, the slit width or the slit spacing by doing the inverse of that. So if it's 1,000 lines per millimeter, then it's 1/1,000 millimeters per line, or 0.001 millimeters. So on that screen, each line is 1/1000th of a millimeter apart. That's what that's saying. All right, now the bulk of this problem is dealing with two yellow lines from a sodium lamp. So you take a sodium lamp, it glows yellow. You put that through a diffraction grating, that yellow light through a diffraction grating, and what you'll see is two yellow lines. If that screen is 1 meter away, one yellow line will be 72.88 centimeters from the central max, and one will be 73.00 centimeters from the central max. We go to the tangent equation, okay? And I'm calling these just to keep them straight. One is YA and YB. So YA is the first order maxima that corresponds to this line, and then we have the first order maxima corresponding to this one. Okay, so we're going to get two angles, one for A and one for B, line A and line B. All right, and we plug in their Y values, and they both have the same 1 meter L value. And we get the angles in radians, and they're not the same, right? So they're slightly different. We can take the angles and plug them into this d sine theta equation to figure out what the wavelength is. Since we know d, and now we know the angles, now we can calculate the wavelengths. So take each d, multiply by the sine of the angle, and you should get these answers. So wavelength A is 589 nanometers, wavelength B is 590 nanometers. So that 1 nanometer difference in wavelength corresponds to a slightly different location of the two lines. This is how we can use diffraction gratings to our benefit. We can take light from a source like a sodium lamp, put it through a diffraction grating, and all the component wavelengths are there will spread out. Even if they're only different by 1 nanometer, they'll be in a different location. And so we can pick out exactly what wavelengths are contained within each element or gas or whatever it happens to be. Everything has a unique signature. It's sort of like a fingerprint for it. It's spectral fingerprint. And in sodium, its spectral fingerprint is notably, or most notably, these two yellow lines that are very close together but clearly distinguished.